Yes, go ahead.
That's correct. So thank you for the introduction. I'm Omri. I'm a PhD student from the Hebrew University. And in this talk, I will present our development and certification of proof checker for deep neural network verification in Imandra. And this is a joint work of us at the Hebrew University, Heriot-Watt University, University of Southampton, and Imandra Company. And before I'll begin, I wanted to thank Remi Desmartin, who is not present here in the conference, but is the main engine behind this work. And nothing here could have been achieved without him. So I'll begin. And standing here in 2025 makes it almost unnecessary to say that deep neural networks are everywhere now and that they're very successful in accomplishing many results. But many people are not very sure of them because unlike traditional software, they are opaque functions. They're trained over a large set of input and output examples, and they're not entirely built as traditional software. And this combination makes neural networks in particular be vulnerable to undesirable behaviors, which are hard to predict and potentially could be very dangerous or costly. And the main example that we have in mind is what we call adversarial examples, in which we have an image that is correctly classified by some neural network classifier. But if we perturb it by a little in a way that the human eye cannot perceive, then it might lead to misclassification. And that is, of course, very undesirable. Then we would like to ask, is it possible to rule out this kind of errors, or at least have the guarantee to find those if they exist? And in order to address this question, the verification community has developed a variety of verifiers that are based on a variety of techniques. And this community currently faces several challenges. And I argue that one of them is the reliability of the verifiers. They're implemented towards performance. They use floating point. And like any other software, they might contain implementation errors. And of course, that may compromise their soundness and undermine the basic concept of verification. So what can we do about that? We can try to formally verify the verifiers, but that might turn out to be a very difficult task because it's a complex software. And instead, what we could do is that we can use proof certificates that the verifier constructs during verification, and then they accompany their results. And the certificate could be checked by an independent checker that we could trust, hopefully, and it would either witness the correctness or reveal the errors. And this is a very common practice. I'm sure most of you are already familiar with that. And in order for all of this to work, we need the proof checker to adhere to a higher standard of reliability, which in our case, what we do is we implement and verify it in an ITP. So our model of trust would look like this. We would have a neural network verifier. It will receive both a neural network and a specification. And then it will either emit a violation, violating counterexample. And this counterexample could be easily evaluated over the network. This is not new, and this already exists. Our novelty here is in the case of that no violation was found, or there is a guarantee that there is no violation. And then the verifier would emit a certificate that could be reliably checked. And not only we gain reliability, we also gain integrability. We were also able to integrate the verifier in a higher level system verifier. So imagine we have a system that includes a deep neural network, and we want to reason about this system. So the system verifier would call a neural network verifier, which will reason about the neural network. The verifier would emit a certificate, and the system verifier would check it using its proof checker. So it's allowed to integrate it in the system. And before I'll dive deeper into how we implemented it and how we verified it, I wanted to give small background on what we did. And I'll start with defining neural networks. This is by no means a formal definition or a comprehensive one, just something that allows us to continue. We can think of deep neural networks as layered functions that apply sequentially affine and nonlinear activation functions. So we have the inputs, we create an affine transformation of them, apply a nonlinear activation, and so on and so forth, some finite number of times. And one of the most common activation function is the ReLU activation function, which we will assume we use only this activation. And it's a two-piece linear function that has an inactive phase, which means that it's the constant zero for all non-positive inputs, and the active phase, which is the identity for all non-negative inputs. And the verification problem for deep neural networks is a decision problem that when given a neural network, an input property and an output property, we would like to find a violation for this implication. Do I have a pointer here? Does it work? I'll wave my hands, I think. OK. If we can find one, if it exists, we say the problem is satisfiable. And we treat this assignment as a violation, as a counterexample. And otherwise, we say the problem is unsatisfiable. And we can think of it as a compliance of the network with the specification. And for the sake of this talk, we will assume quantifier-free linear properties, as is commonly done in SMT. And we will assume the ReLU activation function. And this combination of assumption induces for us linear and piecewise linear constraints. And therefore, we can think of the verification problem as a constraint satisfiability problem of finding an assignment for a vector of variables such that it's in the kernel of some matrix, and it is bounded from both sides. And of course, we also have the piecewise linear constraints, where for a subset of the variables, they need to have their constraint to be one of the ReLU of the other. And I think an example here could be convenient. Let's take a look at this neural network here on the left. It has two inputs, one output, and two hidden neurons. And we define a very simple bounding boxes property. Then the neural network verifier would reduce this to this constraint satisfiability problem. I don't want to get too technical into the details, but just so you'll get the notion, you can look at the first row of the tableau of the matrix that we use here. It corresponds to the fact that B1, which is the input to the node V1, equals 2 times x1 and plus 1 times x2. And you can see also that both x1 and x2 are bounded between 0 and 1. And using this structure, many verification algorithms search for a satisfying assignment by using LP solvers, accompanied with a splitting approach to handle the piecewise linearity. Schematically, the algorithms would work like this. It would start by invoking the LP solver over the linear part of the query. And the solver might conclude that there is no solution, only to the linear part, and we can conclude unsatisfiability. Otherwise, it will find a satisfying assignment. But then, of course, we need to check if it satisfies the piecewise linear constraint as well. And if it does, again, we can conclude with satisfiability, and we have a counterexample. If both cases do not apply, then the DNN verifier might need to perform a split. Then it will pick one of the piecewise linear constraints, a ReLU, and it will create two subqueries, one for the active and one for the inactive phase. Each one of them encodes more linear information, and then we can reinvoke the linear solver and repeat this process. And you can notice that the splitting approach creates a tree structure to the search, abstract tree, and that the whole query is unsatisfiable if and only if all the leaves are unsatisfiable, because otherwise you would find a satisfying assignment at some point. And also one more important thing is that concluding the derivation of unsatisfiability is performed by the LP solver. And that's important. You'll see that in a couple of more slides. So having this scheme in mind, we can start thinking of how we can produce proofs for such algorithm. And as I said earlier, proving satisfiability is straightforward using a satisfying assignment. However, certifying unsatisfiability is more complicated, and it has a complexity theoretical grounds to it due to the NP hardness of the problem. However, the Marabou DNN verifier, which is a verifier that we develop in our lab in collaboration with Stanford University, is able to produce proofs of unsatisfiability and check them. And of course, the main problem is that both Marabou and its native proof checker are implemented in C++, and we don't trust them. I mean, I personally do, but okay. So how do they? Yeah.
Can this solver typically handle?
So it really depends. This kind, I think, thousands of neurons. There are also incomplete methods that can scale much better, like hundreds of thousands of neurons. So we're going back to the certificate tree. This is an example of a proof of unsatisfiability for a neural network verification query. And in this certificate tree, the nodes represent the case splits that were performed during verification. And each one of the leaves would contain a proof of a contradiction, which is represented by a vector. So we'll cover the leaves first, and then we could assemble to understand how we could check the proofs. So remember that I said earlier that unsatisfiability is derived by the LP solver. And that's why for proving unsatisfiability of the leaves, we can use results from linear algebra. And I'm talking about specifically the Farkas lemma, which probably many of you are familiar with. And it has many variants, but here I will present one of them. And the variant tells us that for a system of equation in inequalities of the form that we use in neural network verification, there exactly one of the two options holds. Either there exists a solution, or there exists a solution is an assignment that satisfies all the constraints, or there exists a refutation in the form of a linear combination of the tableau rows, such that for every bounded assignment of the variables, it will sum up to a negative constant. And then, of course, it could never be zero, and there could be no solution to the system. And not only that it exists, we know, and we showed how it can be constructed during the execution of the verifier. So it is constructed during the execution of the verifier. And the main idea is that a verifier could explore many combinations of the linear constraints until it reaches some unsatisfiable configuration. However, when we have a certificate, it sort of gives us a recipe to get directly to the unsatisfiable configuration. So that means that checking a certificate is considerably simpler than solving the problem. So we know how to prove unsatisfiability of the leaves. And now assembling everything to the proof tree becomes almost trivial. Because in order to certify the certificate, we could traverse the tree. And then for each proof tree node, we would check the splits that they indeed are covering, which means that one of them corresponds to the inactive phase of a ReLU constraints, and the other to the active phase of the same ReLU constraint. And then when we reach the leaf, we can certify them using the Farkas lemma. So now, after covering all of that, we can finally start discussing what we did in this project, how we implemented a certified proof checker. So to begin with, we chose the programming language of Imandra, which is OCaml-based functional programming language and interactive theorem prover. So we could both write function and prove things on them within the same environment. That was very convenient. And it also supports arbitrary precision real arithmetic. And here you can see a small code snippet. You'll see that again, so I don't want to explain what exactly it does, though you might guess already. But here below, you can see how we automated the proof using Imandra. And after choosing our programming language, we needed to represent the proof tree and the query using our types. And we defined an inductive type for the proof tree. It is either a leaf, which contains a contradiction vector, or a node that contains two children and a split. And a split could be a ReLU split, which is what we support now, but it could potentially be many other splits. And then to represent the vectors and metrics, what we did is we created polynomials, which were enhanced to expressions and to a system of linear polynomials. And the reason that we did that is that because it was much easier to reason about these types rather than on matrices and vectors. the main checking function then looks roughly like this. It receives the information from the query and a proof tree node. And then it either checks it if it's a leaf, it applies the Farkas lemma. And if it's a proof tree node, then it checks the split and then recursively checks the children. So we get some structural guarantees for free just from defining this type. And now the main result that we wanted to prove was the soundness of this function, which tells us that if this function indeed returns true, then the underlying verification query is unsatisfiable. And our proof consists of three main components. A proof of the Farkas lemma, or in the direction that was relevant for us as proof checkers. We proved the soundness of type reduction, and we also needed to prove that ReLU splits are covering. So I'll now briefly go through each one of those, and I'll start with the Farkas lemma. And this is a generalized form of the Farkas lemma that is formalized over a polynomial system of both equalities and weak inequalities. And well, the phrasing itself is very similar. Either there exists a solution or there exists a refutation in the form of a linear combination of the polynomials. Here we can choose any coefficients for the equalities, and we need to choose non-negative coefficients for the inequalities. But again, the refutation looks the same. It will all reduce into a single constant, which is negative. And then, of course, it cannot satisfy the constraints here. And this is how it looks in Imandra code. It looks fairly simple. If the system of equation adheres some very simple structural properties, which means that they are polynomials over the variable vector x, and the check certificate function that uses the Farkas lemma tells us that it is indeed a valid certificate, then there is no solution to the system. The second component was to prove the soundness of our data representation. Because we proved the Farkas lemma over a system of linear polynomials, then we needed to show that if that system is unsatisfiable, then so is the original form of matrix and vectors. And this also looks like this. If we reduce our tableau and the upper bounds and the lower bounds into a system, and again, we have some structural properties, and for every x, it is not a solution to the system, then that x is either not in the kernel of the matrix, or it is not bounded by the vectors, which means that it's not a solution to the LP form. So combining these two components, we could finally prove the soundness of leaf checking, which tells us this. If leaf checking returns true, it means that there is no solution to the underlying linear query. And again, in the code, it looks like this. If the checking function checks a leaf, which has a contradiction, then it means that the query underlying it is unsatisfiable. But then, of course, we need to assemble it with the second type of nodes, which is the general node. And for that, we needed to prove the soundness of ReLU splits. And conceptually, what we did is that we said the following. Let's say that we have a node. It has two children. And the left one is enhanced with the linear information of the inactive phase. And the right one is enhanced with the linear information of the active phase. Now, if these both queries are unsatisfiable, this means that the parent query is unsatisfiable as well. Or in other words, there is no third option. And again, this is how it looks in Imandra. Here, I don't want to get into the details, but you can have a look yourself. And of course, it's also open source and it's available. And assembling all these three components together, we could finally prove the correctness of the main result that tells us that if this function tells us, it certifies the proof certificate, it returns true, then the underlying linear and piecewise linear query is unsatisfiable. And again, it looks like this. Yeah. So we have this proof checker that we implemented in Imandra. We were able to verify it in Imandra. And now we also try to evaluate its performance against the original Marabou, both verifier and the proof checker. And the evaluation tells us that, on average, proof checking in Imandra was approximately 5 times slower than it took for Marabou, which is a very good point to begin with. And we believe that the slowdown has 2 main sources. The first is the use of more precise arithmetic, and from that we cannot escape, I think. And the other is that we chose data structures that are more amenable to verification, meaning lists, but they might represent very sparse polynomials. So one thing that we could do, we could optimize the verifier with better data structures. Another avenue of evaluation was the line of code that you can see here that gave us a rough estimate of how difficult was each part of it. You can see that the most difficult parts were the soundness of reduction from matrix and vectors to a linear system. This is theorem 7. And the fact that Rayleigh splits are covering is lemma 14. But after proving that, assembling things into the leaf checking and node checking and the overall soundness, it was much easier. So as for future work, there are 3 main paths that we want to follow. First, we want to integrate this proof checker in a system verifier. Second, we want our proof checker to support some optimization that Marabou supports and produces proofs for, and additional activation functions, because potentially this can support any piecewise linear activation. And last but not least, and this is more of a long-term goal, we want to put the DNN itself into this trust model. We want the certificate to give us formal guarantees, not only on the verifier itself, but also on specific implementation of a neural network. So to conclude, I talked a little bit about neural network verification, how we can produce proofs for neural network verification, and how we can check them. We implemented and verified a neural network proof checker for the verifier. And in the future work, our main effort, which is an active effort, is to include the neural network in this scheme as well. And I hope some of it was interesting for you. Feel free to reach me or any one of the co-authors. Some of them are present here. And our paper and our code are available here. And I guess I'm done, and I'd be happy to take any questions. Thank you. Thank you.